Hey guys, alright, this is the notes video for lesson 4.2. So the first thing you should do is start on this warm-up. So fill out this warm-up. Your interest rate is 100%, which means like R equals 1, if that's of help to you. So try and fill this out best you can. Fill in these boxes, answer number 2, answer B, A and B, and then play this video when you're ready. Okay, so assuming you've had a go, and let's talk about what this is all about. So we're compounding. The interest rate is staying the same, but we're compounding at different frequencies. So if we're monthly, we're doing 12 a year, and then weekly would be 365, and daily, weekly would be 52, and then daily would be 365. So my interest rate per period would be that 1, right? But divided over 12, or that 1 and divided by 52, and that 1 and divided by 365. So as a percentage, it's 8.33%. It's 1.92%, and it's 0.274%. So if we evaluate this, we'll get that principal value, which is always 1, and then we're going to multiply it by this growth rate, right? 1.083 or 1.0192 or 1.00274. And we're going to raise them to the 12th or the 52nd or the 365th. Okay, so yeah, my growth rate is getting smaller here, but I'm raising it to a larger power. That's what compounding is all about, right? And so that equals roughly 2,612. Then it equals 2,688. Then it equals 2,714.8. So what's kind of happening here? Okay, well, the more I compound, right, the bigger the number's getting. So yeah, so that makes sense because I'm including more of the growth in my interest rate, right? So that's good for me, right? The more compound, the better. So the question 2 is like, well, could this triple the money? Sorry, when this says 2, there should be a decimal point here and here and here. Sorry about that. There should be a decimal point there. So sorry, ignore that 0.8 here. Could we triple the money? So we started with $1 and we got to 2. In our best case scenario, we were at 2.7. If we kind of kept building this up, would we get to 3? And so I mean, you could basically like play around with this a bit and say, well, what if I did? What if I compounded 10,000 times, right? And so that would be, it would be 1 times 1 plus 1 over 10,000, but it would be all to the 10,000. So we can do that in the calculator, and we would get 1 plus 1 over 10,000 to the power of 10,000. We get 2.718. And you could basically follow the same pattern, right? You could just keep going bigger and bigger and bigger. I mean, I could do 100,000 with the same thing for 100,000, or a million even. So a million, why not? And I could raise that to the power of a million, and I get the same answer. So the answer is no, right? We're not going to get to 3. I mean, you can see that a million was a little bit bigger than the 10,000 that we did. But what we're basically saying is that that the best we can do, like if we compound continuously, is this 2.718. That's the best we can do. And this is important, right? This number that we get from basically making our n really, really big This is E. This is the number E, also called Euler's number, and this is where I want you to transition to your notes. So go ahead and get your notes out now, and we will finish. We'll go from there. Okay, so we're here. We're at the number E. E is this value when we take that 1 plus 1 over n to the power of n, and essentially, like, we're plugging in a massive number. We're saying, okay, well, what happens when n approaches infinity? What happens? Well, this approaches this number 2.718 ... and that number is E, or Euler's number. So this has like a direct application to compound interest, which we'll talk about shortly, but it also has like a lot of other applications in math, and it has a very unique property in calculus, which we'll also touch on. Okay. But this is E. This number. We set n to infinity, and so this is what the value that we approach. And this is the idea that, okay, if we're continuously compounding, this is our real growth rate for that year, right? And so, okay, let's move on from there. Okay, so how do we find E on the calculator? So this is some basic calculator skills. So there's second ln, or second and then the division sign. Both of those will get you E. Get you E in some way. So second ln is E to the power, and then second division sign is just the value of E. Okay. And so I'm pause the video for a second. Just let's make sure we're on the same page. Please evaluate these expressions. Okay. I'll play the video. You can check your answers with me. You should get 2.718. You should get 7.389, 1.65, 0.368, 23.14, and 15.15. Okay. All right. So that's just using E in the calculator. Then we can graph. So same idea here. Pause the video if you're as you're following along. Take a second, plug these in for y1, y2, y3, y4, and plot them. Okay, so if you've taken a second to sketch them, now I will go ahead and sketch. So, I mean, this is very similar to what you did in the previous exponential lesson. Like, these aren't like wildly different, or they don't look wildly different than the other exponentials you've graphed. We have like the same rough shapes, and we have the same ideas with transformations. Like the main key points, right, are like that it's going to intersect the points 0, 1, and if it was just e to the x anyway, e to the x will intersect 0, 1, and then 1 comma e. Like, those are the 2 points that you know are it's going to intersect. And like, it's kind of harder to write because it's kind of hard to draw because the E is not like an integer, right? So it's just kind of hard to actually plot those points. So don't worry or stress too much about getting exact. But this is just reminding you of how these exponential functions look and what these transformations are, right? So we have this left shift and this shift down. We have this reflection over the y-axis and the reflection over the x-axis. Okay. All right, we're on our last page here. So logistic growth. So this is an application of how E can be used. This is called a logistic function. And so the why this is used, and just like for your reference, we're talking about a concept, but you don't necessarily need to be super stressed about this being like knowing the details of this. Okay, so like what is this all about? If we just had if we were trying to model like the growth of population and we use an exponential, the problem with exponentials is that they just go up forever, right? So if you want to kind of set a cap on it, that's where logistic comes in, because logistics, they increase at that kind of exponential rate, but then they peter out and they reach this kind of like stasis. There's a horizontal asymptote, so they don't just keep going to infinity. That's why we can use logistic growth. And so in this case, we're talking about rabbits that exist. We have this function, and we can plug this in right here, like so. Right here, I used the alpha and the x to get that sort of fraction to show, and then I'm going to do zoom 0 to kind of show roughly how this graph looks. Okay, and you can see it's kind of following that rough trend that I graphed over here. And if we go to the table and I plug in like what's happening after 0 years or 1 year or 2 years, or 10 years or 100 years, you can see that the population increases, but it flattens out at 2000, right? So 2000, right, is our max population, and that's called in biology the carrying capacity. Okay. All right. So that's again, this is a way that E can be used, but where you're going to see in your homework is with the compound interest. So before we used this formula, we had A of t equals P1 times 1 plus R over N to the NT. And essentially what's going on here, like this is compounding like quarterly or year or daily, etc., right? Like it's discrete. So we say quarterly, monthly, etc., right? Well, when we want to compound continuously, and again, like the concept of that is like you're including every second of growth that your money has, you're going to take that's going to be included in your growth rate of your interest. Okay, so rather than it happening every 4 times a year, you're just always doing it every moment that your money's growing. You're like, okay, well, I'm going to take the new percentage of that amount and the new percentage of that amount, rather than 4 times a year. Okay, so this is where we use that the E value that we found in really simple terms. That E is substituting out this 1 plus 1 over n to the n, part of this, and we get this new equation that's called PERT, and it's specifically for continuous compounding. So where P is the principal, and the R is still the rate, and T is still the time. Everything's kind of the same, except there's no 1 plus R over N aspect of it, right? And so if we were to apply this using this situation after 1, after 2, after 3 years, and I wanted to find A of 1 and A of 2 and A of 10, that would equal 10,000. All of them are going to be 10,000. 10,000. But then E to the 0.1 times 1, and then E to the 0.1 times 2, and then E to the 0.1 times 10. And these would equal 1151.71, and then 12 to 14.03, and then 27 182.82. So it's kind of the same way that you use the previous formula, but it's a little bit simpler even, because you're just using that E value and not the 1 plus R over N. Okay. So the last thing I want to cover is just like some of the homework questions that you're going to get. You've got these problems that ask about APY. So I want to kind of talk about like what is the difference between APR and APY, and then like how do we find APY. So like APY is like a standardized, so we have APR. APR is kind of like your raw interest rate before compounding, whereas APY is the like post compounding yearly interest rate. Like why does this matter? If I told you like, hey, like, and we'll look at this example, like we have an 8.9% APR, but I'm compounding daily, I can't compare that with an 8.9% APR that's compounded monthly. Like those are going to be two different like real numbers. And so the way that we can compare like an 8.9% APR that's daily versus an 8.9% APR that's monthly is by finding the APY, and that's what I'm going to teach you right here. Okay, so we have $9,300, and it's earning 8.9%. Okay, so we're going to set up this 1 plus 0.089 over its daily 365 to the power of 365t. Right, that's our function. So we already did this first part, right? A function showing after 2 years. Okay, we did that, and then it says also determine the growth rate per year. So like, what is the actual growth rate per year? And so the way that we find that APY is all we do is we take this coefficient, that 365, and apply that to the value here. I'll show you what that means. So first I'm going to simplify the parentheses. So we're going to have 1 plus 0.089 divided by 365. And then, so that's going to be, this is really 9,300 times 1.0002 to the 365t. And then what I'm going to do is I'm going to kind of, you want to imagine it kind of as 9,300 and then 1.0002 to the 365, but then all of that to the power of t. So you can think of it distributing, but you're applying that exponent just to the 1.002, and so we get 9,300 1.093 to the t. So my APY is actually 9.3%. So even it's an 8.9% kind of raw interest rate, but because we're compounding daily, that ends up with a 9.3% interest rate per year. So that's why when you're comparing interest rates, you want to compare that APY, not the APR, because that can be misleading. Okay, we're going to call it there.